Hi! In this video we will create a simple chatbot that will encode users' input into Morse code. But our bot will not only respond with a text message with dots and dashes, but also have a physical output, in the sense that it will blink the resulting code with a diode on the microcontroller. We will use Dialogflow to get the interface for entering our queries. Our webhook, which will be encoding the query, will be written on node.js, and the code for our ESP32 board will also be written on JavaScript using ESPRUINO framework. I always admired people able to create some hardware stuff. It seemed like some magics for me. And in this mini hobby project, I had my first acquaintance with microcontrollers on the example of a ESP32 board. Mine is called Wemos Lolling, or actually Loing 32. Got it from a friend who in turn bought it on AliExpress for something like $4. Our backend will consist of two parts. One will be an ordinary Node.js server, which will work as a usual webhook for our Dialogflow bot. It will handle the webhook requests, encode users' queries into Morse code in the form of dots and dashes, and respond to Dialogflow with this text. But in addition to that, it will also prepare a special array with information for how long to switch the diode on our microcontroller on and off. And alongside with a response to Dialogflow, it will make a request to our board sending this array. The code on the board will provide connection to Wi-Fi and implement a simple web server to get the request from our main webhook server, and also will contain the logics to blink with a diode. We will start with creating the Dialogflow part of our bot and the webhook. Next, we will look into what Morse code actually is and how to encode data into it. Thirdly, we will write the code for our ESP32 board, and finally we will test how this system works. So let's start with Dialogflow. We will go to Dialogflow console and create a new bot, which can be called something like Morse Chatbot. It will be very simple. We will go to the default welcome intent and map the existing phrases or a new phrase with sys.any entity type. And we will switch on the webhook at the bottom of this intents page. We could also delete the default welcome intent and leave only the default fallback one. Just in case, let's switch on the webhook in default fallback intent too. That's almost everything that should be done on Dialogflow. We still have to fill in the URL of our webhook server in the fulfillment tab, and also we will be using the web demo integration as a web interface to enter our queries. We will return to this a bit later. Now let's create our webhook server. The link to GitHub of this project will be below this video. Let's create a new folder, which we will call Morse Chatbot. As our webhook will be on Node.js, we will type npm in it and install the dependencies which we will be using, namely Express, .env extended, body parser, actions on Google, Axios, and also NodeMon. Also, we will install ESLint with supportive dependencies and Prettier. Let's create index.js file, and back to the package JSON, let's add an Npm script to launch our project with command npm start. we will be using node.mon for running our code. In index.js, we will require and load our .env file, which we will create soon. Import express and body parser. Then we will create a new app by calling express and set up body parser. Next, and also we will add the .slint rc.js file with slint settings. Next, we will initialize a variable called port and set it equal to the value from environment via variable port. Let's create a file .env and enter port equal to 3001 here. And finally, we will add app.listen, port, and console log that our app has started on the specified port. Next, we will create a folder roads with an index.js file in this folder. Here we will import express and create a new router. Let's create a tested endpoint /health. We will add a router get method which will respond with status 200 and a string OK. We will export our router. And back to the index.js file in the root of our project, we will import roads and make our app use these roads. Let's use ngrok to expose the port 3001 from our local PC to the world. So we got a publicly accessible HTTPS URL. Let's launch our server and make a GET request to health endpoint to confirm that the basic Express.js server is working. Now let's add a webhook for Dialogflow. In roads folder, let's create a file df.webhook.js. Here we will import Express and actions on Google packages. We will create another Express router. Next, we will create a Google Actions app and pass a settings object to it with debug false and client ID, taken from the environment variable client underscore and ID. Client ID can be taken from the JSON file saved from Google Cloud Console. To do this, you need to go to Dialogflow, click on the gears icon to the right of the bot's name, and in the General tab, click on the service account link. There you should search for the service account name from Dialogflow, click on the three vertical dots to the right, and save the key file in JSON format. Open it and copy the client ID. Back to df.webhook.js, let's add a handler for webhook endpoint and use our actions on Google app for this. And let's export this router. In index.js file in roads folder, let's import df.webhook and write router use df.webhook. In df.webhook.js, we will write some code which can be found as an example in the documentation for actions on Google packages. Please see the link below the video. What it means is that for any intent, we will have one logics written in the default block of switch case. And for now, here we will simply echo what user has said, adding uSaid before the input. Now let's test how our webhook is working with Dialogflow. Let's copy the URL we got from ngrok, go to Dialogflow Fulfillment tab, enable the webhook, and in the URL field we will enter our ngrok URL /webhook. Then we will switch to Integrations tab and enable the web demo integration. Here we will get a link to open our web demo. And let's send some queries to check how our webhook endpoint is working. By the way, just to mention that ngrok has a nice web interface which allows to see the requests which are coming and the payload which is passed. So at this stage we created a very simple chatbot on Dialogflow with a webhook which echoes users' inputs. Next, we need to write an encoder to Morse code. Actually, there are some ready solutions for that in the form of npm packages or APIs. But we will create this bicycle from scratch. Plus, anyway, we would probably need to customize the code which will prepare payloads for our microcontroller. So, using the article on Wikipedia, let's write our Morse encoder. Let's create a folder helpers and index.js file in it. Let's save our Wikipedia article URL for reference here. We will add a variable .length msec. This will be the main parameter used for calculating others, such as dashes length and intervals length. Let .length msec be equal to 100 milliseconds. Then we will add a variable between symbols of same character msec equal to .length msec. Our dash length msec will be 3 times longer than .length msec. Interval between letters in milliseconds is also 3 times longer than .length in milliseconds, and interval between words is 7 times longer than the length of a dot. For our text response returned to Dialogflow, we will create, so to say, graphical representations for dot, dash, and intervals in variables .graphWrapper, dash graphWrapper, interval between letters graphWrapper representation, and interval between words graphical representation. Now let's write Morse code for the English alphabet and numbers. I used variables s equal to .length msec for dot, for short signals, and variable l, long signal, equal to dash length msec. And the alphabet will look like this. Now let's write a function called encodeWord. It will prepare 2 arrays, word signal lengths for our microcontroller and word graphical representation for Dialogflow. We will take each symbol of the word, and if such symbol exists in our Morse code object, then if this is not the first symbol, then we need to add an interval between letters. And for each character, we will be creating an array of signals called one-character signal lengths. If this is not the first symbol of the character, we will be adding an object with key of and value between symbols of same character msec, milliseconds. And then for each symbol of the character, we will be adding the following object. For example, for letter S, we have 3 dots, so we will have an array with the first element, an object with a key on equal to 200 milliseconds. then an element with a key off equal to 200 milliseconds, and then again on 200, off 200, and finally on 200. Then we will use array spreads operator, 3 dots, to merge our existing array word signal lengths and an array 1 character signal lengths, filled for each character. And for graphical representation of each character in the word, we will replace numbers that correspond to dots and dashes with the values of variables .graph representation and .graph representation correspondingly. And also, we will add symbols for each character to the array that contains symbols for the whole word. Then, we will write another function encode phrase, which will take a phrase and also return two arrays with signal lengths and graphical equivalents, this time for the whole phrase. We will split the phrase into words and iterate over this array. If this is not the first word, we will add interval between words. We will use our function encodeWord to encode each word and merge the resulting arrays for each word into the final arrays for the phrase. And finally, we will export the function encodePhrase. And now let's use this function. Let's go to df webhook.js, inroads, and import encode phrase from helpers. We will take conf query and encode it, saving the result to the variable phrase in Morse. And we will respond by conf.ask phrase in Morse graphical representation. As this is an array, we will join its elements via a period. Let's test this using the web demo form. Now it's time to write code for our ESP32 microcontroller. To write any code on your microcontroller, you need to connect it to your computer and set up the corresponding IDE. These steps may differ a bit depending on the operation system and software you have already installed in it, for example Python and some Python libs. I won't describe this process in detail, but will only mention that in my case it was not very smooth, and I remember that I had to install several Python libs, install the USB driver for the board, and solve some problems with access to the USB port. I will post links to some articles that were useful for me during this process under the video. We also need to flash ESPRUINO firmware on our board, which is described on the ESPRUINO.com website. So let's assume that you have successfully set up the software development environment for your ESP32 board and flashed ESPRUINO on it, and have ESPRUINO web IDE working. Now it's time to write the code. First we need to connect to Wi-Fi. For this, let's import Wi-Fi module, set our SSID and password, and then connect to Wi-Fi by writing wi-fi.connect and then passing the SSID as the first parameter, an object password with a password, and a function and a callback function, where we will write to our console the output of function wi-fi.getIP. Here we should get the IP of our board printed to console. If not, you need to find out what's the problem. Sometimes settings on the Wi-Fi router may prevent connecting. Remember the IP your board is getting, as we will need it later. Let's also wrap our Wi-Fi connect into a special function on init, which will be called each time the board is connected to power supply. And also let's add a call to the special function save in the end to save the code to the flash memory. Now let's write a function which will blink with a diode when the board has connected to Wi-Fi. This function will switch the built-in diode on the pin 5 on and then in 1 second switch it off, after 2 seconds again on, after 3 seconds off, and finally after 4 seconds it will switch the diode on. Here you can see that when I power on the board from the power bank, it quickly starts to blink our sequence, indicating that it has connected to Wi-Fi. Next, let's launch a web server on this board and make it switch the built-in diode on and off when we, for example, make GET requests to the IP address of the board /on or off correspondingly. In the function on init, after indicate connect function call, let's add a const http require http to import the http library, and then http.createServer server handler listen on port number 80. Server handler function will take request and response objects and then remove the slash from the request URL to get the words on or off. And if command is on, then we will digital write LED1 on, and if off, then we will write digital write LED1 0. After that we will respond with res write head 200 and with a text response. Let's deploy this to the board and test. As you can see, the diode is switching on or off when we make requests to the IP of the board /on or off. Next, let's write a function blink, which will take an array of objects with on or off signal lengths, which we'll call on-off script. Let's also create an object LED_modes map, which will map on to 0 and off to 1. In blink, we will get current timestamp and then get the number of milliseconds from the beginning of the Unix epoch. We'll also create a variable to store the index of an object from on-off script currently processed. We will send the first signal from on-off script, which should always be on immediately. And then we will calculate the time when the first signal should end by adding the value from the first object of on-off script to the start time. Then we will use setInterval function to check for time every 1 millisecond. So every 1 millisecond we will get current number of milliseconds since the beginning of the Unix epoch, and if the end of previous signal has come, saved in next step imsec variable, then if this is the last element of on-off script, then we will switch off the diode and clear interval. Otherwise, we will increment exec index variable by 1, get the key for the next element, and LED mode for its value. and then switch the diode to the received LED mode. And recalculate the next step IMSEC. We also will update our server handler function. The array with signal lengths, which will determine the behavior of the diode, will be passed in the body of a POST request. We need to receive this data by chunks, parse it, and then call our blink function, passing the received array, which will be the value of the key called Morse script. Now it's time to deploy this code to our board and check it. We can use Postman for making such POST requests. Now we should add sending requests to our board from our webhook server. Let's go to df webhook.js in routes and import Axios. In our handler for any webhook call, let's add Axios post. The first parameter will be the IP of our board, which we will be storing in .env file in the variable ESP32 IP. And the second parameter will be an object with a key Morse script and value phrasing Morse.Morse signal lengths. And we will add handlers for a successful request and for error. Now let's test this by sending different messages via the web demo form and watching how our board blinks with the diode. From here we can customize our hardware output, for example by attaching a bigger diode to the pins of the board, as is shown at the beginning of this video, or by attaching a speaker for sound signaling. So this is it. Hope you liked it. Please see the links to this project's repo and other resources mentioned below this video.